In this recording, we're going to learn how to create exponential equations. I know here it says exponential equation. Let's go ahead and put an S on the end here, make it plural. All right, so we've done a lot of work with linear equations, and they have constant rate of change, right? Constant slope. And we've also looked at exponential growth and decay, but here we're just going to kind of look more generally at this concept of an exponential function. So here's an example of one. F of x equals 8 times 2 to the x. That's how we pronounce it. So we're going to evaluate each one of these different y values. This is a y value here, right? If you were to enter this into your calculator, you'd put y equals 8 times 2 to the x, right? That's how you'd enter it. And so what we're going to do is evaluate that particular y value for this particular value of x. It's f of x, so therefore this is an x value, this 2. Okay, so let's substitute 2 in place of x and evaluate what the y value is. So we do it like this, 8 times 2 raised to the power of 2, because that 2 is the x value. Now just do the math. Got to do the exponent first, right? So 2 times 2 is 4. 4 times 8 is 32. And then so it says, indicate what point must lie on the graph. Well, this is a y value, right? We said f of x is a y. So it's the y value when x equals 2. So we'll write it this way, 2, 32. And we put parentheses around it because it is a point. Like you do evaluate f of 0 and f of negative 1. Then play the recording when you're ready. All right, so hopefully you took time to play that pause and work those both out. So it would be 8 times 2 to the 0 and 8 times 2 to the negative 1 power. Well, anything to the 0 power is a 1. So it's really like 8 times 1, which is 8. So that gives me the point 0, 8. Something to the negative 1, let's just kind of do a little think bubble here. So 2 to the negative 1 means 1 over 2 to the positive 1. Okay, a negative exponent means the base appears in the denominator with a positive exponent. So it's like, I'll just show the work here. 8 times half is what it means. We know that half of 8 is 4. So we've got the point negative 1, 4. Now it says use your calculator to draw a sketch of this function in that particular window that is indicated. So they're giving us a pretty big y scale, pretty big y range. Not too much in the x because these things grow fast, right? Again, we're graphing the function y equals 8 times 2 to the x. Okay, and we saw from our growth work that just means things are being doubled every time, right? So we're starting out with 8, and we're going to 16, 32, 64. It's growing fast pretty quick. So let's grab our calculator. Let's put into our y equals. Clear out whatever's in there. Put in 8 times 2 to the x. All right, and we also need to change our window range. So our x minimum went from negative 4 to a maximum of 4. And our x scale is fine. Our y minimum went from negative 10 to a maximum of 130. Why 130? Well, let's look at our table for a second and see how this is growing. So we said we were going to go 8 and then double that to 16, double that to 32, double that to 64. By the time we get to a x value of 4, well then the y value is 128, which is just under 130. So I think a y max of 130 will accommodate up to this point here, 4, 128. So we're just going to make our sketch back over here. Oh, we never saw the graph, did we? So let's look at the graph. Going very slowly, then it starts to take off. If we were to look back at our table, we can see that things are growing kind of slowly in the negative values of x, right? A quarter, a half, a 1, a 2, a 4. They're kind of all close together. Even 8's not too much compared to 130, but then it starts to really take off on the right side of the graph. That's where we really see that exponential growth. So we're just going to make that sketch back on our paper. Okay, 4, if you remember, was only like a half. And then by the time it got to 10, by the time it got to 0, it was about there. And by the time it got to 4, it was more like that. Now in terms of making that graph, it hugs the x-axis, and then it starts to slowly increase. Then it rapidly increases the last little bit. Shouldn't look quite vertical, but that's a sketch, right? It says draw a sketch. So we did our best. We didn't plot all the points. We would have gotten a better idea if we merely plotted points. So now let's speak about what exponential functions do. They're all about multiplication. We saw that right in the table. Let's check out our table one more time just for reference point. The y values are being multiplied. Every time the x's go up by 1, the y values get doubled. So they're not going up by a constant amount, going up by a factor of 2. All right, so an exponential equation will look something like this. Y equals a times b to the x. A is the y-intercept. Okay, we saw that. That would be like 8 on our graph. And that's the number, that's the coefficient here. And b is the base, or the multiplying factor, the growth factor. So we keep multiplying by 2. And I think we can see that, right? We can observe that. Okay, for our example 2, I would like you to work out parts A and B, because I think you have the background to do that. Find out g of 0, tell us what point that indicates, and then find the values of g of 1 and g of 2. Play the recording when you're ready. All right, I'm hoping you took time to do that. Work this out relatively quickly. G of 0. Anything to the 0 power is 1, so that just gives us 54, which means the point was 0, 54. G of 1 means we're going to substitute 1 in place of x. So 1/3 of 54 is just 18. And then g of 2, I'm going to substitute 2 in place of x. So that means we have 1/9, because you square the 1 and square the 3. So I'll just show that work. It's like 54 times a 9th. Well, you know what 54 divided by 9 is, right? 6. So there's our y value. Part C asks us to make a sketch using our calculator in this window, -2 to 4, -100 to -10 to 100. Okay, well, what's our y-intercept? The question asks us to label the y-intercept. Well, that's the place where x equals 0, right? And we already found that out in our work. So in our part A, right? So it looks like the graph starts when x is about, it's about 100, when x is like 2/3 or so, -2/3. And then it starts to level out once it gets past 2. So let's make sure our graph features those things. So that was going to be 100, -10. We do want to label our scale. So that's -2 to 4. Y-intercept of 54 would just be a little more than half. About there. We said the graph's going to start 1, 2, 3, 4. So right about here is where the graph started. It came down through 54. And by the time it got to 2, it wasn't doing very much. Because remember, this graph is a take 1/3 each time. Let's look at our table real quick. Okay, so we don't know much about these numbers, but we can do 54 divided by 3 is 18. 18 divided by 3 is 6. Divides by 3, divides by 3, and so on. So it's a multiply by 1/3 or divide by 3 sort of behavior. So that's what we call exponential decay. Asks us why this function is always decreasing. Okay, so what I've said here is each time the x increases by 1, the y is multiplied by 1/3, which is the same as dividing by 3. We saw that in the table. So how will I know if the function is going to increase or decrease without looking at the graph? So I'd like you to make some observations between examples 2, which was right here, which ended up decreasing. How would you have known that wasn't going to be a decreasing or decaying function? And example 1, how would you have known this was going to be a growth function? See if you can generalize there, and we will make some summary here in the box. Or hopefully you recognize it's going to grow if b is greater than 1, but if b is between 1 and 0, b is going to decrease. Obviously, if it's negative, weird stuff's going to happen, but we have to have a positive base. But if it's less than 1 and positive, it's going to decrease or decay. So we're going to skip number 3 for now and focus on number 4. So I want to find a function based on the table. So kind of go in the reverse direction. We don't know the values of a and b, but we do know their behavior. Let's just summarize. A is our y-intercept, and b is our base or multiplying factor. Okay, so identify those two things, please. Find out what the y-intercept is. Find out what the multiplying factor is. Okay, so hopefully you took time to do that. The y-intercept is always when x is 0, right? So we have it right here, our y-intercept. It's when x equals 0. All right, well then, and so the a value is 10. And next, we need to know what our multiplier is. So let's use a different color here. I see times 3. Times 3. So as long as the x's are going up by 1, the y's have the same multiplier or factor, times 3. So all that means is the b, the base, is 3. Now we can put it all together. So we can say the y equals the a value, the initial amount, times the base, as many times as you want it to happen, right? So if I'm going to go out to the 4th value of x, I'm going to be multiplying by 3. 1, 2, 3, 4 times, right? That's what exponents are. It's repeated multiplication. All right, let's finish with this one final example. It was easy for us in our last example to identify the multiplier as 3, right? It went 10, 30, 90. That was easy stuff for you. This one, not so much. It goes 32, 48, 72. It's not obvious what we're multiplied by. Clearly it's increasing, so we know we've got a b value that's bigger than 1, but it's not obvious. So maybe we can find out the initial value, right? Maybe that would be something. So the initial value is really when x equals 0, right? That's our y-intercept. So that's no problem. We can pick that out right there. It's 32. Okay, and again, let's now make a point to ourselves that means the a value is 32 in the form y equals, if we're speaking about, let me put it over here, our generic exponential y equals a times b to the x power. The a is 32. Cool. So as the x's increase by 1, what's the y value multiplied by? Not obvious. So here's how we figure it out. We do 48 divided by 32. Let's back up and show how that works. if I do 30 divided by 10, I get 3. 90 divided by 30, I get 3, and so on. So if I can't find what the multiplier is by inspection, I do 48 divided by 32. So we can grab our calculator or our head and maybe simplify that and realize it's 1.5. All right, so now I think I'm multiplying by 1.5 each time. I can test it for this one. Is 72 divided by 48? Yep, that's 1.5. And so on. It does look like it's a times 1.5 times 1.5 times 1.5. Okay, so now we know our b value, so 1.5. So let's say what it is. B is 1.5. What's our percent growth? Well, that goes back a couple lessons, right? We said if we were growing by 2%, we would have a multiplier of 1.02. So if we have 1.5, what must be our multiplier? Right, 2%, 1.02. 23%, 1.23. Well, that means it's 50%, right? So finally, we have the function that models this. So we're going to start with y equals, like our model here. We need our a value, which said is 32. And then our b value, 1.5, to the x power. And there's our function that models this relationship. Of course, if I wanted to, I could put that in my y equals, and I could look at my table and see that it behaves this way. Thanks for watching.